Hi everybody, this is Amanda Amos, and today I'm going to talk to you about what a concept-based curriculum is and share some of my experiences teaching a concept-based curriculum as an IB or International Baccalaureate chemistry teacher. So to get a quick picture of what a concept-based curriculum is, I would advocate that everyone get the handout shown on the screen here. It's a free PDF that you can download. It's called Getting the Big Idea, Concept-Based Teaching and Learning. So we want to know what is concept-based instruction and then how we can actually implement it in our own classrooms. The thing that I like about this document, first of all, it's really short. And then the other thing that I really like about it is down at the bottom, there is a nice template that a teacher who's new to a concept-based curriculum could take and use to design units in his or her own classroom. And I don't want to spend a lot of time talking about that template, but I did want to point out to you that it's there in case you wanted to go back and look at it and implement it later on your own. So first, let's go back up to the top and talk about what is concept-based instruction anyway. And so to answer that, we can look at this definition. Concept-based instruction is driven by, and here's the main point, big ideas rather than subject-specific content. Not that we don't teach subject-specific content, but that all of that subject-specific content is couched in terms of the big ideas. So we specifically reiterate big ideas over and over to students in our classes and in other classes where those big ideas repeat themselves so that students have a broader understanding overall of that concept. Let's see. Another thing to point out is what is a concept versus what is a subject-specific content idea. And again, this document provides some nice examples. So for instance, we can take an example in a lit class of talking about surrealism. So surrealism is one form of symbolism. So surrealism is a subject-specific content strand, while symbolism as a whole is a big idea. And students might talk about surrealism, and then they might change in their English lit classes and talk about a different form of symbolism, and then they might go to their math classes and talk about how we use symbols in math to represent equalities or inequalities. And then they might go to a science classroom and talk about models and symbols in that classroom as well. So over the course of that student's education, he or she would be talking about different forms of symbolism over a variety of disciplines with the goal of having a big picture of what symbolism is by the end of his or her education. There are some other concepts or big picture ideas shown here. I just wanted to point that out to you to give you some examples. Mainly today I wanted to focus on the diagram here because I think it gives us a better understanding of what a concept-based education is and how we can implement it as teachers in our own classrooms in a way that doesn't feel scary or intimidating and that doesn't feel like we have to totally redo everything in our classrooms. We don't have to start from scratch to implement some concept-based teaching and learning. All right, so now let's look at this diagram a little more carefully. The thing that I really like about this particular diagram is that it shows us right away that when we implement concept-based instruction, we are not doing away with content-specific standards. In fact, those are right at the heart, right at the center of concept-based instruction. So right here in the middle are content-specific standards. I'm going to talk to you later about the implementation of big ideas And to do that, we're going to look at some of the IB chemistry and biology standards. So I'm actually going to pull out the documents from the IB organization, and we're going to look at some of their specific standards that they expect students to know and to be able to do. Okay, so those are at the heart of concept-based instruction. But then outside of that, we also want to be talking about bigger ideas, repeated big themes in the sciences. So the concept that I want to explore today through the standards is a really important one in the scientific disciplines. It's the relationship between structure and function, okay? So our concept is structure, function, relationships. So over and over throughout the sciences, regardless of whether you teach chemistry or biology or physics or environmental science, there is the repeated theme that the way that something is shaped, the way that it is built, affects how it functions. And it is likely built the way that it is so that it functions the way that it does. And so we'll look at some specific examples of that through the chemistry and biology curricula, and then talk about how a teacher or a group of teachers could make sure that the content knowledge and the concepts are linked. And finally, after we talk about content knowledge and skills and concepts, the last piece of a concept-based instruction is an action piece. And that's kind of our assessment, our culminating plan for determining what students know and letting them express their knowledge. So the action is the last step, and I'm going to give you an example from IB Chemistry and Biology called the Group 4 project. So that's going to be our action phase. All right, so let's take a look at the guidebook produced by the IB organization about the chemistry instruction it expects for students. Okay, so this is a page from the IB Chemistry Guidebook provided to teachers, and essentially it outlines the standards that students are to be taught. Okay, so the first thing I want us to notice is that at the top of every page, there is a nature of science piece similar to the front material in the Georgia Performance Standards that describes kind of the big idea. And then underneath the big idea, there are very specific elements that students are supposed to know. So if we look at the big idea, this important piece is right here. It says scientists organize subjects based on structure and function. The periodic table is a key example of this. So here I have a big idea that structure and function are related, and I have a more specific example. The periodic table is a key example of this. So now I know when I go into my classroom, I'm going to teach how the periodic table is laid out, but I'm also going to talk to students about the fact that this is an example of a structure-function relationship. So let's take, for example, a discussion about the elements in group 17 on the periodic table. That would be these elements here. They're called the halogens: fluorine, chlorine, bromine, iodine. And notice that they're located right next to each other on the periodic table. That is purposeful. Again, the periodic table is a place where structure and function are related. Then, if I draw diagrams of what these atoms look like, so you can see that here at the bottom, that's their structure. I might ask students, what is it that all of these guys have in common? And a person who's looking carefully at these pictures might soon discover that regardless of which element I'm talking about in my halogens row on the halogens column on the periodic table. The thing that all of these elements have in common is that they have 1, 2, 3, 4, 5, 6, 7 electrons in their outermost energy level. So if I look at chlorine, 1, 2, 3, 4, 5, 6, 7 in the outermost energy level. And the same is true for all of the halogens. So that is a structural feature that these elements have in common. I might then point out to students that all of these halogen elements are extremely reactive. So all of the halogens are very reactive. That is a function. And then as we discuss the halogens more carefully, we might learn that the reactivity, the high reactivity, is related to the structure. The idea that there are 7 electrons in the outermost energy level, when these atoms, to be most stable, would have 8 electrons in their outermost energy level. So the fact that they're missing an electron, and they're essentially searching for it to make themselves more stable, is what makes these elements very reactive. Okay, so that's an example of a structure-function relationship. And I'll teach that structure-function relationship, but another thing that I'll do is specifically point out to students, this is an example, one example of many in the sciences about a structure-function relationship. So this is a continuation of that same big picture idea that I've been talking about in the IB chemistry syllabus. And I just wanted to post this particular diagram to show you that at the end of every big idea in the chemistry syllabus, there is a link to where else this big idea might appear. So IB has specifically gone through the curriculum, and not just the chemistry curriculum, but the other science curricula, and cross-linked recurring topics and couched them in terms of big ideas. So that appears down here. So I know that this idea that reactivity is based on electron configuration, the location of electrons within an atom. That idea is going to be covered again in chemistry when I get to option A, not that you know what that is, but I'm going to talk about why plastics biodegrade, and when I teach that, I know I need to come back to this big idea. I also know that when students take IB biology, they're going to cover this idea when they get to topic 2.3, the 3D structure of molecules. So the biology teacher knows when I'm teaching important content to her classroom and vice versa. So we work together to reinforce big ideas. It's one of the things that I really, really like about the way that the IB standards are laid out. It makes it very easy to establish connections and big ideas. It's done explicitly in the curriculum. So later in the year, after my chemistry students have talked about what atoms look like and how the structure of an atom determines its reactivity, we start putting atoms together to make molecules, and then we get to some organic chemistry. Here's another page from the IB chemistry guide when we talk about the shapes of organic molecules, and here again we see this big idea. The three-dimensional shape of an organic molecule is the foundation pillar of its structure and often its properties, its reactivity. So there's that big idea again. And when we get to that big idea, I want to talk to the students about how it's one of our big ideas. So the specific content that I'm trying to teach, based on the slide that I previously showed you, was the idea that some molecules are what we call chiral. They're mirror images of each other. So if you think about a non-chemistry example, your hands, your left hand and your right hand, can be thought of as chiral. They're mirror images of each other, and you can't make your left hand look like your right hand. You can't turn those two hands in such a way that they identically match each other. So that's the idea of chirality, and that idea happens in molecules as well. So there are molecules that are made up of the exact same atoms, but those atoms are arranged in such a way as to be mirror images of each other. And no matter how I rotate one, I can't make it look exactly like the second, just like my hands. So I need to introduce that concept to students. It's really important to medicines, for instance. Often medicines, one of these mirror images will be the drug that has the desired benefit of taking the medicine, and the other one causes harmful side effects. But it's really hard to separate the two when you're making this compound. And so often drugs are a mixture of these two guys, these two mirror images, and one does harm and one does good. So that's an example of a content-specific standard that I need to teach. But when I talk about this, I also explicitly want to say, okay, let's get back to our big idea. So I want to remind students that this is an example of a structure-function relationship. That the way that these molecules are built determines how they act, how they behave. And I want to specifically point out to them that they've seen that idea before when we talked about the structure of atoms, and that they'll see it again before the year is over. And then they'll see the same idea again in biology. And by explicitly stating that to them, I'm building that big idea in their heads so that they can transfer it to new situations. All right, now let's look at an example from biology. So while I'm talking to students about the relationship between the structure of atoms and molecules and how they behave, how they react, our IB biology teacher is simultaneously teaching students about other structure-function relationships within cells, within tissues, and within entire organisms. So this is a page from the IB Biology guidebook. And again, we've got this essential idea here. So this was, the topic is human physiology, and within this, they're talking about the digestive system. And the big idea here is that the structure of the wall of the small intestine allows it to move, digest, and absorb food. Again, our structure, so there's the structure piece, affects how that organ functions, move, digest, and absorb food. So when our IB biology teacher reads that essential idea, she has to think to herself, okay, so I'm going to teach how the small intestine works, but I'm also going to point back to that big idea and show this as an example of a structure-function relationship. So when our IB biology teacher is examining or teaching the small intestine, she might have students look at a picture of the small intestine and first of all notice its structure. Notice all of these little folds and creases. They might talk about how all of those folds and creases create lots of surface area. And then they might talk about how nutrients are absorbed through the small intestine, and the idea that the more surface area there is, the more nutrients that can be absorbed. So again, this is the way that the small intestine is built, its structure, its foldiness, its bendiness, creates a greater functionality in the small intestine. So this is just one example of many, many in biology of a structure-function relationship. So after I, as the IB chemistry teacher and the IB biology teacher and I have explicitly taught several structure-function relationships, some very specific content, what we then might want to know is, can students transfer the structure-function relationship idea to a new situation. And so to test that in sort of a formative way, one of the things that we might do is just go take a walk outside, and we might look at a tree, and we might ask students, why is a tree shaped like it is? Why is it built like it is? So what is the purpose of having, for instance, a big trunk? Why are the leaves, the individual leaves, shaped like they are? So why are they textured? Why are they veiny? Why are they broad? Why are they ridged? Why do they point to the sun? And then we might just listen for a while and engage in a conversation with students about why it is that the structure of the tree determines how the tree functions. But rather than explicitly teaching students facts about trees, we would rely on their prior knowledge of structure-function relationships to start as the springboard for this discussion. All right, so now let's go back to our model of what concept-based teaching and learning looks like. So we've covered in pretty good detail the fact that content includes our standards, and then we couch that content within bigger concepts. In this idea, or in this example, we're looking at structure-function relationships. And then finally, let's look at this action piece. So after we've explicitly taught some of this content, and we've allowed students to practice looking at examples of structure-function relationships on their own, it's finally time for a culminating activity to demonstrate their mastery of this big idea. And for us, we do that in something called the Group 4 project. Okay, so now let me explain to you a little bit about what the Group 4 project is and how we implement it. So the Group 4 project is an interdisciplinary science project that our IB chemistry and biology students carry out. The IB chemistry and the IB biology teachers meet, and we come up with a general theme for the year. So, and often our theme matches one of our big ideas. So maybe our theme for a particular year is structure-function relationships. And then we put students into interdisciplinary groups, so mixed groups of biology and chemistry students, so that they have a broad variety of experiences and expertise and examples of different structure-function relationships to bring to the table. So we put them in these interdisciplinary groups, and then we announce the theme to them. And then we have the students ask a question, a research question related to that year's theme, and then they design and conduct an experiment to answer their specific research question. We have the students keep a blog of their experiences related to their project, and so what you see on the screen here is an example of one student's blog, or one group of students' blogs, and there's a whole lot of information here if you ever want to go read about it, but we'll stick to the abstract of their blog. So when they were all finished, they wrote an abstract kind of summarizing what they found. And so the important pieces of the abstract are, first of all, well, what research question did they come up with? So we can find it sort of stated not as a question, but as an actual statement here. Their goal was to look at essentially the greenness of a leaf. So the amount of chlorophyll within the leaf, so that's the structure piece, how much how much chlorophyll the leaf contained, and then relate it to the rate of photosynthesis of that particular leaf. So that would be the function piece. So does the greenness of a leaf determine the rate at which it can conduct photosynthesis? So these students came up with that question on their own, and then they designed an experiment to test that, and that involved measuring the greenness of different varieties of leaves by extracting the chlorophyll from the leaf, and then measuring its greenness using a colorimeter, and then also to measure the rate of photosynthesis, trying to look at how much carbon dioxide the leaf absorbed using a carbon dioxide monitor. Okay, so they gathered data, and then they decided at the end, their conclusion was that overall there was a slight increase in the rate of photosynthesis as the level of transmittance increased, so as the amount of chlorophyll increased. But the results were very scattered, and they could neither support nor refute their hypothesis that greener leaves would photosynthesize more. So to summarize our IB curriculum, or our concept-based curriculum, we do in fact teach specific standards within our disciplines. However, we do so within the umbrella of broader concepts, and the broader concept we talked about today was structure-function relationships. And then our assessment piece is an action step where students get to use their knowledge of the broad concept to apply it to a new idea. So that's our summary of a concept-based education. If you have any questions, I'd be happy to talk with you more about it through our course discussion threads. And thank you so much for listening.